All right, welcome here to this lesson on scale diagrams, where we're going to take a look at how do we compare scale diagrams. We look at a scale factor and how that will affect the way that we calculate those kinds of things. We will come up with an equation for that as well. And so let's jump right in and do a little bit of some preview stuff. So starting off with scale diagrams, what is a scale diagram and how can we use scale factor in order to do that? Well, a scale diagram is an exact replica that has been enlarged or shrunk to display or play with better. Okay, so we have a whole bunch of things that we could use as scale diagrams. The first one, it's a map. Yeah, okay, this is a map. It happens to be Steinbach, where I am located. And this town right here is not actually, tiny. Yeah, it's huge. Yeah, it's big. Okay, maybe not huge, but it's a lot bigger than this map shows. But I can see what it looks like on this map. It's been shrunk, okay, at a proper size so that everything looks the same distance away as it would be, just a lot smaller. Okay, so the distance from top to bottom has a similar factor as the distance from left to right in real life. Okay, so we can kind of use that in order to understand that scale. Another one, this is something that we might play with, is little vehicles. Yeah, okay, these are not an actual size, but they look exactly like the original. Exactly. Okay, just they are a lot smaller. Okay, easier to play with, easier to put up on your shelf. You can use them as a talking piece. Okay, so those are a couple things that get scaled down. Something that gets scaled up. Sorry, there we go. Went back there. Okay, anybody know what these are? Yeah, these are cells. Okay, from the looks of things, they are plant cells. Yeah, at least that's my understanding. Okay, these cells are not actually this size. They have been expanded. Okay, much bigger. They look the exact same as they are, but they have been made bigger. Everything about it has been made bigger so that we can actually see them. We can't see them if they are super teeny tiny and microscopic unless we make them bigger. And that's what this diagram has done. It's made everything bigger so that we can see what it exactly looks like. All right, so a scale model resembles everything about the actual thing, just at a smaller or bigger rate. These cars in this picture here, they look exactly like the original, but they are just much smaller. Everything about them looks exactly the same. If we could get a array that would make everything bigger, okay, a large array or whatever you want to call it, it would be the exact same car, just had been enlarged, right? So it's just been shrunk down to this size. All right, the amount that every dimension is adjusted is based on what's something called a scale factor, and that scale factor is exactly the same for every single one. You will notice on the video, the picture, each one of those little cars has a scale factor. 1 to 18, 1 to 24, 1 to 43, 1 to 64, 1 to 87. These scale factors tell us by how much it has been shrunk. Okay, how much smaller is it than the original? That's our scale factor, and we can use that in order to solve questions, okay, and come up with solutions. So, like I said, the 1 over 24, this represents that for each 1 unit of the model, the actual car is actually 24 units. So if the car is 1 foot long, the actual car is 24 feet long. Now, it might not be exact, and that's okay, but that's what it's telling us. For every 1 inch of dimension on the car, it's 24 inches on the actual car. Okay, so the one that it has been modeled off of. Okay, scale factor we have is 1 over 24. Okay, and we'll talk about how we can come up with that in just a little bit. Let's take a look at an example. Okay, we'll do a few examples and then I'll get you to try some questions on your own. So here's the example. A fire ant is 8 millimeters long. Okay, nice and small. Okay, thankfully, we don't want those things to be big. A giant model of the ant uses a scale factor, or a K value, of 200. How long is the model of the ant? Well, we're going to take our actual dimension, actual length, and we'll talk about that in a little bit. We're going to multiply it by the scale factor of 200, and so the actual length is 1,600 millimeters, or 1.6 meters long. Okay, that's huge. Okay, it's bigger than I can, about that big. Okay, it's massive compared to that little tiny ant. It's 200 times bigger. Yeah. Okay, so that's kind of what we're talking about when we're talking about enlarging things. Now, to solve these problems, we're going to use this formula right here. Our scale dimension, Okay, so our model is equal to the actual dimension times the scale factor. Okay, so scale dimension, and then scale dimensions on this side here, then actual dimension, and then scale factor. Okay, I get flipped around a little bit sometimes. That's how we're going to describe this, or our equation. We're going to use this over the course of scale diagrams as well as area and volume a little bit later on. Now, this equation is a lot of words, so I like to simplify it. So I'm going to simplify it to SD is equal to AD times K, K being our scale factor, AD being actual dimension, and SD being our scale dimension. All right, determine if the following scale factors give a bigger or smaller scale, so a little bit extra. If we have a K value of 1/3, it's smaller because K is less than 1. So therefore, it's going to be a smaller version. It's going to be a third of the size. If we have a 12, bigger. Yeah. Okay, that's going to definitely be bigger because it's bigger than 1, so it's 12 times bigger. Now, what about 1.8? Yes, it's got a decimal, but it's above 1. So in other words, this is still going to be bigger, just a little bit bigger. Not quite double the size, but a little bit bigger. And 50%? Well, 50% is a percentage that is smaller than 1. Okay, and so therefore it's going to be smaller, and that is going to be half the size of the original. Okay, so that's just something to kind of be aware of and think about. All right, I'm going to move myself over. Ooh, there we go. That was a lot of fun. I can even do some loop-de-loops. Yeah, no, I won't do that. Here's some examples. I'd like you to solve this example. What is the wingspan of the model, okay, based on the scale factor and the actual wingspan? And then, once you have that, unpause the video and we will see how you did. All right, let's go through this question. Let's see how you did. First of all, we want to figure out what information we have. We are given the actual wingspan of the fighter jet, so therefore that's going to be our AD. Okay, our actual dimension, not our model dimension. That's what we're trying to find. Then we're given our K value, which is 1 over 100. I'm going to leave it as a fraction. If you want to put it as a decimal, you gladly can. It's 0.01. And then we put it into our equation. So our scale dimension is equal to our actual dimension times our scale factor. 13 times 1 over 100 is 0.13 meters, or the same as about 13 centimeters. So we went from a jet that would be wider than the class to a jet which is that big. Yep. And would actually be able to fit, and we could actually take a look at it. Okay, it's a scale model. Okay, now we only talked about the wingspan. We didn't talk about how long this jet was. All right, question number 2. Give this one a shot. Pause the video. Come back when you have your answer. All right, we have the model of a TV. It is 10 inches long, and the real TV is 60 inches long. What scale factor was used when making the model? Well, what do we know here? So here's our equation. We're going to rearrange it a little bit to solve for K, because we're trying to find what our K value is. So we have to take our scale dimension divided by our actual dimension. And this is important. We know what our scale is. We are told the model is 10. That's our scale. The real is 60. That is actual. Okay, real, actual, model, scale. So when we plug that in together, we get 10 over 60, which simplifies down to a K value of 1/6. Therefore, the model is 1/6 the size of the original. Okay, so that's a lot smaller, right? It makes it a lot smaller. All right, here's another example. We have Kipling, Saskatchewan has the world's largest paperclip on display in their park. It is 15 feet long. If the scale factor used to make it was 180, how long was the actual paperclip? Okay, what do we have? We have our scale dimension. Yeah, we've got our scale dimension and we have our K value. So we need to rearrange this in order to figure out what is our actual dimension. Divide both sides by K, we're going to get our actual dimension is scale dimension divided by our K value. So 15 feet divided by 180, and we get our actual dimension of 0.0833 feet, which if we do a little bit of conversion becomes 1 inch. Yeah, 1 inch. That's the size of the actual paperclip. But the model is 15 feet wide, which is about half the class. So it's a decent sized paperclip. All right, what is the scale factor between these two triangles? Are they proportional? And I'll talk about proportional once you find the scale factor. All right, solve for it. Unpause the video when you have your answer. All right, let's see if we can find our scale factor. Now, the first thing I'm going to do is figure out which one's actual, which one's scale. And usually the first one's actual, the second one's scale. So that's what I'm going to use. Now, I want to use a matching side. So I'm going to use the left-hand side to figure out what a scale factor is. And scale factor is equal to scale dimension divided by actual dimension. So 3 divided by 6, and we're going to get a scale factor of 0.5. And you're like, hey, Mr. Barkman, what if we'd use the other ones? That's a good question. Let's use the other ones. There we go. Okay, let's use those. Same thing, scale, actual. 5 divided by 10 is 0.5. Now, you'll notice we got the exact same value. If it's actually proportional, and this is where that word comes in, then every single comparison or a k-value needs to be exactly the same. The k-value between the left side and the bottom side was exactly the same in both situations. Therefore, it's proportional. Well done. Yes, these ones are. Are these ones proportional? So what's the k-value, and are they proportional? Pause the video, come back when you have your answer. Okay, what I'm going to do first, actual scale. Make sure to do that. Take matching sides, 8 and 4. There we go. Figure out the k-value. We have 4 over 8, 0.5. There we go. There's a k-value, right? Well, does everyone match that? Well, yeah, the right-hand side does too. It's 8 and 4 as well. But does the bottom match it as well? Well, let's see. So let's go with the bottoms now. Same thing, 3 divided by 5, scale factor of 0.6. Is it the same as the 0.5 we saw earlier? No, they are not similar triangles because their k-value is not the same for every single piece. So it's important that we see that, important that we can recognize how we solve for that. All right, that's the end of the lesson. Thank you so much for watching. I hope that this scale factor thing works. Remember that you can use your formula. You can look at the rearranged formulas as well and definitely use those. And maybe put those on your cheat sheet for your test. That could be really helpful. Yeah, I would say so. All right. Thank you so much for watching. Have a wonderful rest of the day.